Today, we'll explore the core skills that physicists use every day, including how to design experiments effectively, take precise measurements, and apply the scientific method to solve complex problems. This will give you a clear understanding of what it takes to succeed in this exciting field. Let's get started. This slide shows how the scientific process moves from making observations to developing laws. We start by noticing patterns or trends in the world around us, which gives us a foundation based on real experiences. From these observations, we create hypotheses or models. These are provisional explanations we can test. The next crucial step is falsification, which means while we can never prove a theory with absolute certainty, we can disprove it with a single valid counterexample. This cycle continues through experiments and validation to refine or reject ideas, eventually leading to well-supported theories and laws. This approach helps ensure that scientific knowledge is reliable and always open to revision based on new evidence. Let's explore how science moves from what we observe to establishing laws that explain natural phenomena. It starts with observations and patterns, looking closely for trends or unexpected behaviors in the world around us. From there, we form hypotheses and models, which are provisional and testable explanations designed to make sense of those patterns. Testing these hypotheses through experiments is crucial, but what really strengthens scientific understanding is falsification. This means a theory can never be absolutely proven, but it can be disproven by a single, verifiable counterexample. When hypotheses survive rigorous testing and potential falsification, they contribute to broader theories and laws that summarize our understanding. This cycle of observation, hypothesizing, testing, and validating helps science progress steadily and reliably. Now, let's look at how isolating variables works in practice using an example with stationary waves on a string. Imagine we're investigating how the frequency of these waves changes when we adjust the tension in the string or its length. Here, the tension is manipulated by changing the hanging masses, which we can easily control, while the length of the string is another independent variable we might alter. The frequency of the wave, which we observe as a result, is the dependent variable. To make sure the results are valid, we have to keep other factors constant, like the mass per unit length of the string and the environmental temperature. If we fail to control the mass per unit length, say by switching to a different string type during the experiment, it would mess up our findings and make it impossible to accurately link tension to frequency. This example shows why careful control and isolation of variables are crucial when studying relationships in experiments. When discussing health and safety, it's important to distinguish between hazard and risk. A hazard is something that has the potential to cause harm, like a Class 3B laser, which inherently carries danger. Risk, on the other hand, refers to the chance that the harm will actually happen, such as the risk of retinal damage from a stray laser reflection. It's not enough to rely on generic risk assessments. Physicists have a legal obligation under cost regulations to develop point-of-use texts, which tailor risk assessments to the specific conditions in their labs. This means assessing factors like whether local fume extraction is adequate, or determining the right shielding protocols for ionizing radiation, ensuring safety measures are practical and effective for the actual environment where the hazards exist. Let's take a moment to clarify the difference between accuracy and precision, which are key concepts in measurement. Accuracy refers to how close a measurement is to the true or accepted reference value. For example, if you hit a target near the bullseye, your measurement is accurate. On the other hand, precision is about the consistency of repeated measurements, meaning how closely those measurements cluster together regardless of whether they are near the true value or not. The image shows this clearly with two targets, one where the shots are all close to the center, illustrating accuracy, and another where the shots are clustered tightly together but off to the side, illustrating precision. Additionally, resolution is an important factor to understand. It's the smallest interval that an instrument can measure, like 0.5 millimeters on a fine ruler. This resolution sets the limit for how precisely you can make a single measurement and affects the uncertainty in your readings. Understanding these distinctions helps us improve how we measure and interpret data in any scientific or practical context. Let's take a closer look at experimental errors, which can be divided into two types: random errors and systematic errors. Random errors are unpredictable fluctuations that cause variation in your measurements, making it harder to get consistent results. These affect precision, but you can reduce their impact by taking multiple measurements and averaging them out. On the other hand, systematic errors cause consistent inaccuracies because of flaws in the method or equipment, which impact accuracy. Unlike random errors, simply repeating measurements won't fix these. Instead, you need to recalibrate instruments, adjust the method, or apply mathematical corrections to address these errors. Understanding these differences helps us improve both how precise and how accurate our experimental results are. Now, let's look at an example of spotting systematic error in practice. Imagine using a micrometer to measure the diameter of a metal cylinder. If the micrometer shows a reading of 0.12 millimeters when the jaws are fully closed, that's a zero error, a kind of systematic error. This means any measurement taken will be off by that amount. For instance, if you measure the diameter to be 5.50 millimeters, the true diameter is actually 5.38 millimeters once you subtract the zero error. Because volume calculations depend on the cube of the radius, not correcting this error will significantly affect the final result. It's important to understand that repeating the same measurement many times won't fix this issue. The only way to get accurate results is through calibration or applying a mathematical correction to account for this zero error. Let's look at how to quantify uncertainty in measurements. Every reading has some margin of doubt, which we call absolute uncertainty. This is the raw amount that might be off based on the instrument's precision. For example, if we measure something as 115 millimeters with an uncertainty of plus or minus 2 millimeters, that uncertainty is the absolute amount. To put this in perspective, we calculate fractional or percentage uncertainty by dividing the absolute uncertainty by the measured value. Using this example, 2 divided by 115 gives about 1.7%, which tells us how significant the uncertainty is relative to the measurement. When combining measurements through multiplication or division, such as finding volume from length, we need to add these percentage uncertainties together to understand the overall uncertainty in the result. This process helps ensure we interpret our findings with the right level of confidence. Now, let's take a closer look at how we analyze the data graphically. The graph here shows the relationship between the dependent and independent variables, with a line of best fit representing the trend. The gradient of this line tells us the rate of change, how one variable changes in response to the other, following the equation y equals mx plus c. The intercept is also key. If the line doesn't pass through the origin as expected for a directly proportional relationship, this can indicate systematic errors in the data. Additionally, the uncertainty bars around each point help us understand the range of variability or potential error in our measurements. By looking at these bars, we can draw lines for the maximum and minimum possible gradients to determine the overall margin of error in our results, which helps in assessing the reliability of our analysis. Let's take a closer look at how to spot anomalies within our data. The graph here shows a clear relationship between two variables, with most points lying close to a straight line, indicating consistent behavior. However, there's one point that stands out, far from the expected range. To determine whether this is a true anomaly, we follow a three-step decision process. First, we identify if the point significantly deviates beyond the acceptable margin of error. If it does, we move on to investigate the cause, considering whether it's just a random fluctuation, a failure in equipment, or perhaps something new and physically meaningful. Finally, we must justify how we handle this anomaly. It's important from a scientific standpoint that anomalies are not deleted without careful reasoning. Any decision to include or exclude such data needs to be thoroughly documented and supported to maintain integrity in our analysis. This structured approach helps ensure that our conclusions are based on reliable and transparent data handling. When evaluating your results and drawing conclusions, it's important to start by checking whether the outcomes align with your initial hypothesis. This helps confirm if your predictions were accurate or if they need revisiting. Next, you want to place your results within a broader scientific context by comparing them with established reference values or accepted findings. This shows how your data fits within the current understanding. Lastly, it's crucial to acknowledge any limitations in your study, including uncertainties, methodological weaknesses, or assumptions made along the way. Being transparent about these factors reminds us that no conclusion is absolute and encourages careful interpretation rather than overconfidence. Now that we've explored the core ideas, let's look at how scientific knowledge is built and refined over time. When a single experiment is conducted, it's just a beginning. That experiment first goes through peer review, where other experts check the methods and results carefully to catch any errors or bias. Then, the findings are evaluated against agreed conventions, like standardized protocols or accepted practices, which helps maintain consistency. After that, the terminology used is shared and understood across the field, making sure everyone interprets the results the same way. Only after passing through these stages, peer review, conventions, and shared language, does the information contribute to accepted knowledge. This process filters out human bias and confirms that ethical and safety standards have been met, so what we accept as scientific fact has gone through multiple levels of scrutiny and agreement. Now, let's focus on the key difference between repeatability and reproducibility. Repeatability means getting consistent results when the same person uses the same equipment and method within a short time frame. This confirms that the measurement is precise and reliable within that specific setup. Reproducibility, on the other hand, is about different people using different equipment and methods at different locations but still obtaining similar results. This shows that the underlying physical law holds true universally, not just due to specific conditions in one experiment. Understanding this distinction helps us trust whether a result is simply precise or fundamentally reliable across various scenarios. As we've seen throughout this presentation, discovery is a continuous journey without a final destination. In physics, every answer leads to new questions, pushing our understanding further and expanding our knowledge. The picture here captures that endless cycle perfectly. Nothing is ever completely settled. We build on what we know while staying open to new experiments that can challenge existing laws. This ongoing process is what drives progress and keeps science alive. It reminds us that every finding is part of a bigger story that's always evolving.